Welcome to the Rich Report, a podcast with news and information on high-performance computing. Today, my guest is from Nvidia. We have Sumit Gupta. He is the GM of Tesla Accelerated Computing at the company. And today, Sumit's here to talk about the Tesla K20, which is their 64-bit accelerator for HPC.
So, Rich, we want to talk to you about the announcements we're making at Supercomputing, and essentially we're announcing the Tesla K20 family of products. I'll get to that in a minute. I wanted to start by something that you know and your audience knows well, which is a couple of things happened over the last few years where scientific computing started demanding, or I should say, science started demanding more and more computing. And a reflection of this is kind of the usage of the NSF teragrid. That's one metric to measure. And at the same time, while we wanted bigger supercomputers and more of them, the challenge that arose was the amount of energy that they required was really large. So around the same time, GPU accelerators came on the stage, and in particular when Fermi launched, I think there was this situation where we had a high demand and this new technology that enabled us to reach that demand or meet that demand. And that's why we saw this takeoff in the number of, kind of in the usage of GPUs in high performance computing. And you can measure it in a number of ways, right? Number of top 500 systems that are GPU accelerated, the number of OEM systems available in the market to deploy, the number of applications, the number of universities, everything has been increasing by 10x, 20x, 50x, right? So really, this was good timing, big demand, and the right product at the right place. Now, we've also talked before about how GPUs are on this regular cadence, right? There's this march of the GPUs. Every couple of years, we come up with a better product, which is 2 to 3 times faster. And with Kepler, we've actually managed to make it 3 times more energy efficient over Fermi. So that's what we're going to talk about, and that's what we're announcing. We're announcing the Kepler-based product family called the K20 family. I'll show you how these are the fastest and most efficient accelerators on the market, how they're powered by CUDA, which is the world's most pervasive parallel programming model, and I'll show you how that comes about. And lastly, how together this really fast accelerator with this really popular parallel programming model are delivering world record performance on scientific applications. So the first set of news. When we announced K20, really there were 2 products behind it. We actually just talked about K20 back then, but it's actually a family of products called K20X and K20. K20X is the flagship high-performance product at about 1.31 teraflop double precision peak. K20 is a notch lower at 1.17. The single precision of these accelerators is actually very important to notice because it's actually 3 times the performance of the double precision. So three times higher single precision over double. This is important because more and more applications are becoming mixed precision applications. So, which means that they try to run in single precision most of the time and drop down to double precision only, or use double precision only when they need to either converge or when they need the accuracy. And then the other data on this slide, including memory bandwidth and the size of the memory buffers on the 2 products. So let's talk about each of these things one by one. Performance, as you can see on this chart, if we measure DGEM, double precision matrix multiplies, which are the basis of LinPack, the K20X is 3 times faster than Fermi, our flagship Fermi. Pretty straightforward math there. And about 7 to 8 times faster than a Sandy-bit CPU. Okay. Now, you can look at performance in a different way, which is architectural efficiency. Whereas Fermi was delivering 65% of the peak performance in DGEM, for certain DGEM sizes, Kepler can actually achieve 93% efficiency compared to its peak. So we enhanced not only the performance, the absolute performance, but we also enhanced the efficiency of the GPU itself in terms of what it delivers in the architecture. The other thing that we found is Kepler is extremely energy efficient. Now, the data on this slide is preliminary data. We're briefing you pretty early in the cycle, so we haven't had a chance to completely vet this data. We're running the benchmarks again, but our early benchmark shows that a K20X based system is going to beat Blue Gene Q on energy efficiency. Naturally, if we do this, it's going to be a big deal. So, honestly, we're running it again just to make sure at this point, and we'll loop back with you to confirm the information afterwards. So, high performance, very good architectural efficiency, and very good energy efficiency. This is really why Oak Ridge chose Kepler to go build Titan. And you must, you saw the news, you reported on this yesterday. This is a 27 petaflops peak machine. 90% of the performance is coming from the GPUs, with about 18,000 K20Xs in there. So we, in our press release, talked about K20 at that time because we hadn't announced K20X, but Titan actually has K20X GPUs in it. In fact, we have such an overwhelming demand for Kepler. We have already shipped 30 petaflops worth of Kepler in just 30 days. And we have a really strong pipeline out there. Lots of customers have pre-ordered, and we continue to receive more orders for Kepler. And it'll be widely available later this month. So that was the first set of news. Any questions on that piece so far?
No, I would just like to take note of that, Sumit. I mean, 30 petaflops in 30 days. It seems to me that not too long ago, if you aggregated the entire top 500 together, you wouldn't have come up with 30 petaflops. So that's remarkable.
Actually, that's a really good point. I mean, in fact, pre-Sequoia, if you remove Sequoia, in other words, a year ago, 30 petaflops was more than the entire top 500, just 1 year ago. So let me talk about the second piece, and I'll talk about how CUDA has become extremely pervasive. Right now, there are 8,000 unique institutions with registered developers at NVIDIA. So, these are just the people we can actually count because they registered on our website as a developer. Typically, I would say there's usually maybe 2 to 3 times the number of institutions of what actually people register. We've had 1.5 million downloads of CUDA and have shipped almost a little shy of 400 million CUDA GPUs since we started our first CUDA GPU in 2007. This is actually 629 courses at universities in 62 countries. And the point I'm trying to make on this is, if you're teaching parallel programming, if you want to teach parallel programming, you have actually 4 choices. The first choice is to use pthreads, which are really, not something you want to start teaching parallel programming with. Everyone will get scared and run away. Option 2 is to use MPI, but MPI is really applicable to cluster applications. It's not a very good single node. If you just want to teach people on a laptop, MPI is not that valuable. OpenMP, which is really not parallel programming because you depend on the compiler to do the work. So you're actually just writing directives or hints for the compiler. And the fourth option, which is the newest option, only 5 years young, is to use the CUDA C or CUDA C++. And the reason it's caught on is because, first of all, we didn't invent a new language. We just used C, C++, and Fortran and added these extensions or keywords that we call the CUDA extensions. So we took an existing language, added semantics to enable you to specify parallelism. So it made it much easier for academic institutions to teach parallel programming on a laptop by just taking a language that the students are already familiar with. And that's one of the reasons why it's so widely taught and used in all kinds of applications. And this is reflected in the application growth we've seen. This year, we're seeing a 60% increase in the number of applications over last year. So we're seeing this acceleration in the number of applications that people are accelerating with GPUs. And this is the who's who of applications, right? These are not small applications. These are commercial applications like Ansys Mechanical, Abacus and Simulia, Adobe CS6, you know, or even the kind of life sciences applications like Amber, Chromax, NAMD. So really widespread range of applications, and the rate at which they're being moved to GPUs is actually increasing. Its success is breeding more success type of thing right now. We are announcing 3 new leading apps that are now GPU accelerated. There is the first beta of Ansys Fluent that will be available eminently on GPUs. MSc Nastran, which is used for structural mechanics, in particular for cars, and Charm, which is a very popular and widely used molecular dynamics application. So again, just to reiterate, right, a lot of application growth, but also these are key apps. These are mainstream apps that are getting onto GPUs. So third set of news is talked about the K20 family, talked about how CUDA is integral to its success and actually its future success. And let me talk about the performance that both of these products put together deliver. These are full scientific applications and speed up of K20X over standard bit CPUs. And what we're comparing here is server to server, CPU server with dual socket CPUs, and a system with dual socket CPUs and 2 GPUs, right? So basically server to server comparison here. And you can see that the speed ups range anywhere from 8x to 32x in all these different application domains. And we took a sample of one application each just to show you what's happening out there. I'll highlight one of these applications because some kind of exciting late-breaking news. WLSMS, material science application out of Oak Ridge, they have been able to achieve more than 10 petaflops on this application, which is actually a record-breaking simulation. The previous record, they won a Gordon Bell last year for achieving roughly 3.1 petaflops on the K. So Titan just barely got done, and they've already kind of scaled and achieved some pretty good performance there. Lastly, on the applications, I do also want to highlight how these applications are scaling to thousands of GPUs. I mean, you asked about Nastran, but here's data on other applications like this material science app called QMC Pack and molecular dynamics NAMD. The QMC Pack is a weak scaling example, and NAMD is a strong scaling example. Strong scaling is harder to do because you're taking the same molecule and dividing it up into smaller bits throughout the entire cluster. So that would be a good example of your Nastran thing. I mean, Nastran takes one model and tries to distribute it, so it's harder to scale those things. But GPU is achieving pretty good scaling. And the other thing you notice here is the slope of the GPU advantage is better than the slope of the CPU. So it actually scales to as the number of nodes increases, the performance benefit of GPUs is higher over CPUs. So that was the main content. I did want to close with kind of closing thought that we believe that we are now in the era of accelerated computing. Titan, I think, is the flagship in this new exciting era. We kind of started talking to you many years ago, and we were um, we started talking about how GPUs can be used as accelerators in HPC, and now we've come to a point where it is a foregone conclusion that moving forward, accelerated computing is the way forward, right? Whether you talk to us or to Intel, at this point, the two leading HPC providers, processor providers, are telling you the same story. So I think this is going to be the next big phase in HPC. So that's it. And this is just a summary of everything we talked about today. We talked about the K20, talked about the apps, and we talked about the record-setting performance on these apps.
Okay, so first question comes to mind. I mean, is the K20X, is that GA this year, or what does that look like?
Right. So we've shipped it to Oak Ridge already, and we are going to basically at this point we're waiting for the OEMs to get it to production. In other words, I can ship right this year, and each OEM is going to have their own kind of schedule. At Supercomputing, all the major OEMs will announce support for both K20 and K20X. The K20 has a channel version, right? It goes into distribution, which will be available within weeks. I mean, by mid-November, we should be in full volume production for the channel version of K20.
Okay. And then just at the highest level, what is the difference between the K20 and the K20X?
Essentially, I mean, the way to think about them is just the performance benefit. I mean, the K20X is the flagship, right? Highest performance that you can, if the highest performance you can have, and K20 is one click down for essentially mainstream performance, right? So it's just a family of products which delivers different performance levels.
Okay, so no form factor difference or major power consumption difference or anything to be concerned with?
No,
okay.
Nothing major.
Okay, cool. So Sumit, you've got your coming out party then with well, you've talked about Kepler earlier in the year with the 32-bit, but the K20 is really that's prime time for you in HPC. And I spent some time with the Titan folks this week who got the first 18 or 19 thousands of your K20X product. Their major concern, it seemed to be, was proving to their community that they could port applications, and they spent a lot of time describing that progress. And when they set out, it was interesting. They said, this was 3 years ago when they started planning Titan. GPUs were not mainstream supercomputer pieces at that point. So they made a big bet. Do you see other institutions doing that same kind of thing for 3 years from now?
Yeah, and Oak Ridge did make a big bet, but they also, one of the things they did was they made sure they themselves and we committed to work together on making sure the applications would be ready the day Titan was built, right? That was part of their investment. In fact, I would say the biggest investment they make is in software. Titan is cheap compared to all the software work that they do for these large-scale systems. GPUs or no GPUs, just scaling your apps. We're seeing a similar type of commitment from all kinds of HPC sites, right? I mean, even if you look at the list of folks who have already committed to the system, right? You see it's NOAA, it's CSCS. CSCS is the Swiss supercomputing guys. Indiana is building a pretty large system. NCSA with Blue Waters, USC, the Shanghai Jiao Tong University, which is actually probably going to be the biggest university deployment of K20 in China right now. So we're seeing this commitment all over the world. You know well that the fastest supercomputers in Russia, India, Brazil, Spain, number of other countries are based on GPUs, and they took that risk too, right? They built it before the apps were there.
Yeah.
Satoshi built Subame before the apps were there because he knew that this was the path forward, and the only way to get the apps there was to first build it and make people move.
Mm-hmm.
Otherwise, inertia is easy to stick to.
Yeah.
So if you want to get to the next level of high-performance computing, you have to make a commitment to accelerated computing at this point.
You know, the question I usually wrap up with is, how hard is it to kick the tires on this? You're seeing the showcase customers. The people are moving this way. It's got momentum, but, you know, how low is the barrier to GPU computing for people that are interested?
I think the lowest barrier, in my opinion, there's three ways, right? You can either start with a library, and there's tons and tons of libraries, and in fact, the library support is increasing every day. That's the easiest. The second method is to use OpenACC, where you let the compiler do most of the work. And then the third approach is to figure out, learn how to do parallel programming, which is more explicit and requires a little bit of rethink about your algorithms and how you map them. And all accelerators are going to be the same, despite everything Intel is talking about in Xeon Phi. At the end of the day, that's exactly the way how you're going to program a Xeon Phi 2, right? By using directives or by using some explicit programming model. At this point, given all the momentum that we have around GPU programming, I think it's safe to say that people will continue to evolve and evolve their programs, and we'll see more and more traction here.
Well, terrific. Well, Sumit, I want to thank you once again for coming on the show today.
Thank you.
You bet. We'll see you at SC12. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on high-performance computing.